There is an identity crisis happening in tech right now, driven by a massive industry obsession with the title of prompt engineer. Calling yourself a prompt engineer made sense 2 years ago, when the job was mostly about crafting clever text instructions for a language model. Today, AI agents perform specific active tasks, booking flights, processing refunds, querying live databases, and making autonomous decisions. When you build software that alters state and takes permanent actions, writing good sentences is the absolute bare minimum. Anyone can follow a recipe, but a professional chef understands ingredient logistics, kitchen workflow, strict timing, and exactly how to improvise when a pan catches fire. Prompt engineering is simply writing the recipe. Agent engineering is architecting and running the entire kitchen. This network architecture diagram shows how the initial text prompt dissolves into a much larger structure. Because building functional, real-world AI agents requires a rigorous 7-layer engineering stack. Treating these agents like simple text generators ensure they will break in production. They must be engineered as resilient, distributed software systems. The first required skill is system design. Functional agents rely on an orchestration of multiple interdependent components. You have a language model making decisions, external tools executing actions, and databases storing the system's state. You must map the exact flow of data between these endpoints. If you deploy multiple sub-agents to handle different operational tasks, you also need strict coordination logic so they do not overwrite each other's work. The second skill is tool and contract design. An agent interacts with external environments through tools that operate on a strict schema defining their inputs and outputs. This diagram shows a central node reacting to a vague contract. When you leave input requirements undefined, the model fills in the missing parameters using its own imagination. Imagination is a fatal flaw when you are processing financial transactions or altering live databases. By wrapping the execution node in rigid schema constraints, defining specific data types, and providing explicit examples, you force that chaotic data into a controlled, orderly pipeline. Explicit pattern matching removes the model's ability to guess. It guarantees the correct formatting before the tool ever executes. Without robust system design and rigid tool contracts, an agent's built-in creativity becomes its biggest point of failure. The third skill is retrieval engineering. Instead of relying on what the model memorized during its initial training, you actively fetch real-time context and feed it to the model. The operational ceiling of your agent is determined entirely by the signal-to-noise ratio of this retrieved data. A digital document is systematically sliced into uniform chunks, balancing detail and broader context. Embedding models mathematically map them, clustering semantically similar concepts tightly together in vector space. Finally, a secondary re-ranking process evaluates relevance, pushing the highest signal data to the top of the queue. If you skip retrieval engineering, you feed irrelevant or garbage context directly into the reasoning engine. The language model cannot self-diagnose bad context. It will confidently synthesize an answer using whatever garbage you provided. Engineering the retrieval pipeline is the only mechanical way to anchor an agent's reasoning in factual reality rather than hallucination. The fourth skill is reliability engineering. You must operate on the baseline truth that external APIs and networks will inevitably fail. This visualization shows a data pulse attempting to reach an external service. When the destination goes down, the agent gets trapped in an infinite loop, endlessly retrying a broken request. To prevent hammering a dead server, you need strict timeouts and retry logic with exponential backoff. You also deploy circuit breakers, which physically interrupt failing paths and reroute data to fallback options, preventing a single external outage from cascading through your system. The fifth skill is security and safety. Once an agent can take real actions, it becomes a highly vulnerable attack surface. A major threat is prompt injection, where malicious users attempt to override system instructions to exfiltrate data. But an engineered perimeter shield shatters against these attempts before they execute. That shield requires input validation to catch and sanitize malformed requests before they ever reach the language model's processing layer. You must also implement output filters and adhere to the principle of least privilege, preventing unapproved actions like unauthorized database writes. Without reliability middleware and strict security boundaries, an active agent is simply an automated liability waiting to take down your network. The sixth skill is evaluation and observability. In engineering, you cannot improve what you cannot measure. When an agent fails, you cannot debug the system without exactly which tool was called, what the retrieval pipeline returned, and the model's exact step-by-step reasoning. This network overlay represents a comprehensive tracing layer. It drapes across the architecture and logs every single micro-decision and data handoff across the system. Tracing transforms opaque agent failures into clear step-by-step timelines that engineers can accurately diagnose. Those traces funnel into evaluation pipelines, testing the actual execution paths against known, verified baselines. From there, you programmatically track critical metrics like success rate, latency per task, and total compute cost. Claiming the output seems better is not an acceptable criterion for pushing an agent to production. Robust observability pipelines replace guesswork with hard metrics, transforming AI development into a rigorous, iterative engineering discipline. The final layer is Skill 7, product thinking. This non-technical discipline is often the deciding factor in whether an agent actually gets adopted. There is a unique UX challenge in designing interfaces for probabilistic systems. The same agent might perfectly execute a task today and completely fumble it tomorrow. This diagram shows a user interface addressing that variability. The interface surfaces the model's confidence levels with visual confidence meters, allowing the end user to understand the system's operational certainty. You must also engineer clear escalation pathways. When the agent hits a failure state, it must gracefully hand the context over to a human operator instead of throwing a cryptic error. Building trust requires setting strict, appropriate expectations, explicitly defining what the tool can and cannot do. Even the most perfectly architected back-end system is useless if the human on the other end cannot safely interpret, trust, or manage its actions. The next time your agent fails, your first response must not be tweaking the natural language prompt. First, audit your existing tool schemas, enforce strict types, and inject explicit examples for every parameter. Second, take one single failed output and trace it backward through the architecture to identify the exact point of systemic breakdown. 9 times out of 10, the root cause of an agent's failure is structural architecture, not semantic phrasing. The prompt engineer launched the AI era. The agent engineer builds the structural systems that make it functional.